All right, let's run through some examples here. Just finding more limits of different sequences, if those limits exist. This first sequence, natural log of n over n, as n goes to infinity, this looks like an indeterminate form. Natural log increases without bound, n increases without bound, and so we can use L'Hopital's rule. The L'Hopital's rule tells us the limit as n goes to infinity of the natural log of n over n is the same as the limit as n goes to infinity of the derivative of the numerator over the derivative of the denominator. So that's the limit as n goes to infinity, 1 over n, which is 0, divided by 1. So that's 0. So that sequence does have a limit. This sequence here does have a limit, and that limit is 0. So that is a convergent sequence, or that sequence converges, and it converges to 0. The terms in that sequence get arbitrarily close to 0. I can get as close as I want to 0 by making n large enough. Those are all different ways of saying the same thing. So let's take the second one. N squared plus 2n plus 1 over 3n squared. I could look at this, and as n goes to infinity, I again have an infinity over infinity. I could use L'Hopital's rule. I'd have to use it twice. It wouldn't be that bad. The derivatives are straightforward. But in this case, I can just recognize that there's balance here in the n squared terms. As n gets very large, well, this is going to approach 1/3. Because as n gets very, very large, it's going to be the n squared terms that really dominate and really matter. And the 2n and the plus 1 are going to be so tiny compared to n squared that they're not really going to register in terms of the limit. So this will get closer and closer to 1/3 as n goes to infinity. So this sequence, this sequence, I guess I should try to write this more properly. A sub n approaches 1/3 as n approaches infinity. Now in this next one, notice the n squared plus 2n plus 1 over 3n squared is the same. So this, looks very much the same. The terms here in absolute value are still going to approach 1/3, but now they're alternating in sign. So now, way down the road, when n is very large, it's like we have a negative 1/3, positive 1/3, negative 1/3, positive 1/3, or at least things that are very, very close to that. And so it oscillates. This one oscillates, and that means the limit does not exist. This doesn't settle down to one limit. It's bouncing around between two numbers, or something very close to those two numbers anyway, so the limit does not exist in this case. Finally, in this last one, we are changing sign again. Right? We have a negative 1 to the n. We're changing sign again, but we're changing sign in things that are getting closer and closer to 0. Right? So if this is bouncing back and forth across 0, it's doing it in a way that gets us closer to 0 each time. So you can imagine negative 0.1, positive 0.01, negative 0.001, positive 0.00001. And we're getting closer and closer to 0, whether it's from the positive or negative side. And in this case, the a sub n approaches 0 as n approaches infinity. So don't think that just because you're changing sign, the limit can't exist. It just depends on what's going on. Are we changing sign and staying away from 0, or are we changing sign and getting close to 0? So those are a few examples. We did one with L'Hopital's rule. We did one where we're looking at a ratio of polynomials. We're comfortable with those limits from Calc 1, hopefully. If not, we may need to review some of these limits from Calc 1, and I can obviously help with that. Just let me know. But those are some examples of finding limits of sequences or showing that the sequence diverges.